Why? Why does my reflection get smaller when I move back and bigger when I move forward? That's strange. I raise my right hand, but my reflection also raises its right hand. Like, shouldn't it be the left hand that's raised?
Quietly, you know what? Unconsciously, they say a flat mirror creates a reflection of the same side. But when I move it, my reflection seems to split. And about the hand thing, shouldn't it be reversed? You're falling for a visual trick. What do you mean? Okay. When light travels from one place to another, for example, electricity, it can both big or even big. And there's this important basic principle called karena principle. Basically, light will choose the fastest path to reach its destination. Oh, it's like it wants to hurry up and arrive, right? You can't say that. No, from that we get the law of reflection. Look at this.
The angle of incidence is the same as the angle of reflection. So, if light comes to the mirror from a solid direction, it will bounce off with the same strength, but in the opposite direction. Let me show you something. Theta d equal theta p. Theta d is the angle of incidence. Theta p is the angle of reflection. And they are always in the same plane along with the normal line. Also, the mirror we usually see arranges plain metal, but glass with a metal coating on the back, like silver. This is to reflect like well.
Why is it that when I look in the mirror, my reflection seems to be behind the mirror, even though there's nothing there? Ah, that's interesting. So, when you place an object or yourself in front of a mirror, light from you reflect to your eyes. But our brain cannot distinguish between light that actually comes directly from the object and light that just a reflection. So, we kind of trade? Yes, our brain thinks, oh, that light seems to be coming from behind the mirror. Even though there's nothing there. That's why it's called a temporal image. It can be seen, but it can't be captured from a screen. Oh, I see.
Now, when we talk about image in a flat mirror, there are some characteristic features that are easy to remember. First, the size is the same as the original object. So, however big you are, your reflection is that big too. Second, the distance is symmetrical from the mirror. If you are 50 cm from the mirror, your reflection is also samely 50 cm behind. Now, third, the image is upright, unlike reflection in water that are sometimes inverted. And fourth, the left and right side are swept. This is what often makes people feel uneasy. When you raise your right hand, it looks like your reflection left hand is raised, but it's just an illusion of our position and how the mirror reflects.
So it's not actually reversed, but because the mirror reflects from a different direction? Exactly. Because the mirror is right, the light reflects directly into our eyes.
One more thing, if the surface is smooth like a mirror, the light reflects neatly. That's called regular reflection. If the surface is rugged, the light reflects in all directions. That's called diffuse reflection.
That's why our reflection is clear in the mirror, right? Exactly. Because the mirror is flat, the light reflection directly into our eyes. Wow, Pete, that's amazing. It turns out we can learn a lot about light just from looking in a mirror. Yes.
Why are there so many things? There was only one earlier. Could it be using forces? Wow, these mirrors are kind of creepy.
Yuza, you are a physics education student. How can you be scared of something like that? This isn't magic, it's physics, Yuza.
When the object is placed between two mirrors that are perpendicular to each other, we assume the object is O.
OA and OB are two rays that come to the mirror Ray OA comes perpendicular to the surface of the mirror, so it is reflected back following the same path. The image reflected to the other mirror and appears in the normal force. Ray OB is reflected by the mirror according to the law of reflection, and the reflected ray is BC. If we extend the ray OA and BC backward, they will intersect at point O1, which is the virtual image of object O formed by the mirror OD and OE are two rays that come to the mirror prime. Ray OD also comes perpendicular, so it is reflected back following its path, appears in the dotted line behind it. Ray OE is reflected into ray EF, also according to the law of reflection. If we extend the reflected ray OD and EF backward, they intersect at point O2, which is the second virtual image of O, this time formed by the mirror prime. The reflected by BC from mirror is reflected back by mirror prime internally, producing ray CG. This ray appears to originate from point O3, which is the image of O1. Likewise, ray EF is reflected back by mirror becoming ray FH, which appears to originate from point O4, which is the image of O2. So we obtain three images when an object is placed between two mutually perpendicular mirrors. You know, it turns out the number of reflection form depends on the angle between two mirrors, and we can calculate the number of reflection using their formula, and 360 divided by theta minus 1.
Ah, really? Is it actually true that it can be proven with that formula?
If you don't believe it, I can prove it. Okay, the result is 3, which means 90 degrees angle, 3 reflection will be formed.
Wow, cool! But I'm still a bit double. Can 3 reflections really appear if the angle is 19 degrees?
It can. Just try it now using the two mirror you have, Yuza.
How do I do that?
It's really easy, Yuza. Just arrange two mirrors to form a 90 degrees angle, then place the object in the front center, and you can see that there are 3 images. For a 45 degree angle, 7 shadows are originated. For a 60 degree angle, 5 shadows are originated. For 120 degrees, 2 shadows are originated.
Wow! So we can calculate the smaller the angle between the two mirrors, the more reflections are formed. Wow! That's amazing, isn't it? This phenomenon is indeed interesting. It proves what we can explain things like this through physics.